In this video, we're going to have a quick review of galvanic cells. You will recall that in a galvanic cell, chemical energy is converted into electrical energy. We're going to have a quick look at the diagram of a galvanic cell and review the key features. Firstly, you will recall that a galvanic cell is constructed of two half cells. A half reaction occurs in each half cell. So in a galvanic cell, we'll have an overall redox reaction occurring, and each half cell can be represented by a half equation. In this example, we're going to be looking at a metal half cell galvanic equation. So basically, if we have our electrodes are two different metals, in this case, say we had copper and zinc, the first thing you need to be able to distinguish is which one is your anode and which one is your cathode. So when it comes down to two metals, you refer back to the reactivity series of metals and determine the most reactive. The most reactive is going to be oxidized, and therefore it becomes your anode. So if we have a look at these two here, zinc and copper, we know that zinc is the most reactive, therefore it will be oxidized, and that electrode will be our anode. Okay, so now I've labelled my electrodes. I've got a zinc electrode and a copper electrode. We've determined that because the zinc is the most reactive, it's going to be oxidized, so it will be the anode. So we know that this one on the left is going to be our anode. Often you'll see the anode drawn on the left of a diagram, but don't always assume that whatever is drawn on the left is an anode. Make sure you go back to the reactivity of the metals. Now, in all electrochemical cells, oxidation always occurs at the anode and reduction always occurs at the cathode. In a galvanic cell, the anode has a negative charge and the cathode has a positive charge. And just to take note again, the anode is the most reactive metal. Now, oxidation always occurs at the anode, so our zinc is going to be oxidized, and in doing so, the zinc atoms in the electrode here are going to be converted into zinc ions in the solution, plus 2 electrons. Now, the electrons can't go into the solution, so the electrons travel through this external wire. So you can see our electrodes leaving the anode, traveling towards the cathode. Also, as the zinc ions enter the solution, we're getting a build-up of positive charges going into that solution, but it needs to be balanced, and that's the role the salt bridge plays. So in the salt bridge, we will have negative ions that will move into the solution. So the negative ions in the salt bridge will move towards the anode in order to balance out the charge created by these positive ions moving into solution. At the cathode, we've got reduction occurring. And so this is probably a good point to talk about the solution in our half cells. Now, the solution in the half cell is called the electrolyte, and it contains ions. So our electrolyte in our copper half cell is going to contain copper ions. So it might be copper sulfate or something like that. And in our zinc half cell, it's going to contain zinc ions. So looking back at our cathode half cell, we've got our copper ions in solution, and they are going to be reduced to copper metal. So we're going to get a deposit on this electrode of more copper. Now, in order for the reduction occur, we need to add electrons to these copper ions, and that's what's happening here. So the electrons that left the anode are going to enter the cathode, come into contact with these copper ions in solution, which will be deposited as solid copper atoms on that electrode. Now, as that occurs, you can see that we are losing positive charges from the solution. So in order to balance out the charge, the positive ions from the salt bridge are going to move into that half cell. Now, the reaction occurring in each half cell can be represented with a half equation. So at the anode, we have got zinc solid from the electrode converting into zinc ions in aqueous solution, plus 2 electrons which travel through the external wire. So you'll notice in this case that the zinc electrode would be eaten away as the zinc in the metal, so those atoms are converted into ions in the solution. In our cathode, we've got copper ions in the solution gaining electrons from the external wire and converting into copper atoms, which will form a solid deposit on that electrode. So the zinc electrode we would expect to lose mass, while the copper electrode we'd expect to gain mass. Now there's a really shorthand way of representing the diagram that we've just drawn there. Basically, you firstly write down the metal of your anode. We do a vertical line that represents a phase boundary. So in this case, it's the phase boundary is between the solid electrode and the aqueous electrolyte, and the change is into a zinc ion. So this is basically telling us the zinc metal is turning into a zinc ion. We then put a double vertical line to represent the salt bridge, and then we use the same notation to represent what is happening in the cathode half cell. So we've got copper ions in aqueous solution, so our phase boundary, copper solid. So this is our shorthand notation to represent exactly what we've drawn in the diagram above. So just to recap some of the important points here, that in a galvanic cell we have chemical energy being converted into electrical energy. The more reactive metal is going to form our anode. Oxidation always occurs at the anode and reduction always occurs at the cathode. In a galvanic cell, your electrons are going to travel from the negative anode to the positive cathode. In the salt bridge, your positive ions are going to migrate towards the cathode half cell, and your negative ions are going to migrate towards the anode half cell. And the reason for the movement of the ions is to balance the charge within the half cells.